All right, so we're back. I think now it's working. I ended up plugging the microphone into this screen thing here, and I think it didn't really like it. But oh well. Okay, so we're back. All right, so we've been talking about just some of the stuff we talked about last time, things like the uncertainty and the contracting aspects of structural design. I want to get into some of the lateral effects that we're going to discuss today. Goodness gracious. Now the remote isn't working. It's going to be one of those semesters, isn't it? All right, so let's talk a little bit about some of the structural load aspects associated with design, specifically wind and seismic. Oh my goodness. Okay. What's that? I think you're right. Hold on. Let's see. All right, okay. Technology is not agreeing with me this morning. Okay. Let's get into it. So we're talking about structural loadings, and specifically I want to get into wind and seismic. Now you all know that there's many more aspects to address, things like dead load, live load, and snow. Between here and concrete design, we'll try and get a general idea of all of them. Now we get our loads from various specifications. It depends on the type of structure that we're looking at. For instance, ASCE 7 is the primary document that we would use to get loads on buildings. But if we were looking at bridges, we wouldn't use ASCE 7, we would use the AASHTO bridge spec. So it just depends on what you're looking at, but by and large, this is one of the most consulted documents in structural engineering to get loads on structures. Now, we're not going to use this directly, but I'm going to go through some of the broad aspects of the document and how to use it for some pretty fundamental calcs. Now, we're talking about wind and seismic, so let's sort of get into that. I showed you this image yesterday to give you kind of an idea of how we address wind and seismic in general in buildings. We don't design the entire structure to resist wind and seismic forces. We only design a certain portion of it. It's kind of like looking at car seats. We don't design the entire car seat to hold you back in the event of a collision. We only design a certain component of it to do so, and we call that component a seat belt. Well, we do the same thing in buildings for wind and seismic. For steel structures, there's really two primary ways that we go about that. One is to use what's called a braced frame. And the idea is to literally just place diagonal braces in certain elements of the structure. Now, if you notice those diagonal braces, they aren't everywhere. They're only in a few key locations, just, again, to resist those lateral forces. Now, if structural engineers had their way, they would keep everything, nice and symmetric, bless you, and place those braces, right in the middle of the building on either side. Problem is that doesn't always work because of the architect and because of the client. I mean, more often than not, the client and the architect don't really want these big, triangular braces right in the middle of the building. So depending upon how the building is laid out, sometimes we have to be a little choosy and a little careful as to where we place these elements. But we have to have them there in some fashion or another. Otherwise, as soon as the wind hit the building, it would just topple over. And I don't think the architect and client would want that to happen. Okay. Now, braced frames are one of the two primary ways that we go about this in steel structures. The other way is to use a moment frame. Now, moment frames have advantages and disadvantages, and the same thing's true with brace frames. With a moment frame, you don't have these large triangular braces in the middle of your base. So it makes your architect and your client happy in terms of keeping open window space and open ingress and egress space and things like that. The downside is that the actual beams and columns that go into these moment frames and the connections that are associated are a little more expensive. For instance, if you look right here on this image, you can see you've got these column lines and these beam lines. If you look right here, see how you've got these stiffener elements right here? You'll see that? That's an additional amount of welding and an additional amount of time that needs to be placed on the fabrication side. Also, you can kind of see just looking at the columns. This is a regular old column that's resisting gravity loads, and then this is part of the moment frame. Can you see the difference between the columns? The columns are much larger, okay? So, you know, you're having to spend a little bit more money on these columns and these beams, but you get a perk that you don't have those triangular braces all over the place. So it's a trade-off, and there's never really a good answer, well, should I use brace frames or should I use moment frames? The answer is it depends. It depends on the loads that you're seeing, depends on the layout of your structure, what you're able to get away with from an architectural or standpoint. So, you know, you really just need to have an understanding of both. Does that make sense? Okay. Now, so let's talk a little bit about loads. So let's get into wind. So wind is, by and large, the most common, or the most prevalent lateral load that we see, because regardless of if your building is in Huntington, West Virginia, or if it's in Los Angeles, you know, you're still going to see wind effects. Now, the thing that makes wind complicated is wind forces and wind pressures tend to get larger as the building gets taller. I'm curious if anybody has been to like to Manhattan or to a place like that. Has anybody ever been on top of the Empire State Building? I'm just curious. Anybody ever been there? Okay. If you've been on top of the Empire State Building, does anybody remember what it was like on that little deck? I don't know about you, but when I was up there, it was fairly windy. Okay. That's one of the things that tends to happen with tall structures, is that the wind forces tend to get larger. This is just a general image of what happens on a structure as the wind gets taller. This is the result of some wind tunnel testing, but in the end, the behavior works quite well. As wind is hitting the building, what ends up happening is the wind pressure gets larger and larger. Another point I'll mention, you actually can get pressures on the other ends of the building. As wind hits one side of the building, you can generate pressures on the other end. You can also, there are also some other sort of quirky aspects with wind. You can generate negative pressures inside the building. For instance, has anybody ever been in a building and it's been a really windy day outside, and you open the door to go into the building or leave the building, and the door either slams shut on you or it blows or it won't stay shut? That's because you're generating pressures inside of the building due to the wind, and that can have an effect on the frame as well, so you have to be able to address that. What I'm really interested in is that you all understand the base wind equation associated with wind pressures. Now, this equation will tell you what is the pressure that is to be applied to a building as a function of wind speed. And one of the interesting things about this equation is that it may not look like it, but this equation is basically Bernoulli's equation. Anybody remember that from fluid mechanics? The way that we derive this equation is pretty straightforward. Ignoring these k constants, which are really just adjustments to the base equation, what we do is this. How does Bernoulli's equation work? You have point 1 and point 2, and they each have different properties, and you're solving for one. So if you have the pressure at 1, what's the velocity at 2, right? You all remember that? Well, the way this works for wind is pretty straightforward. We treat air as if it's our fluid, so we would use the unit weight of air like you would the unit weight of water in Bernoulli's equation. We have 2 points. We have point 1, which is the building, so we're trying to determine what is the pressure on the building due to a fluid, the wind, at point 2 that's hitting the building with a particular speed, with a particular velocity. So we plug in the unit weight of air, and then we throw in a unit conversion to convert a velocity in miles per hour into a pressure in pounds per square foot, and there you go. You get 0.00256 V squared. Those constants on the end are just trying to adjust that base Bernoulli's equation for some real-life aspects. So Kz is the exposure coefficient. What that does, Kz is the one I would say that's the most complicated. What it's trying to do is increase the pressure on the building as a function of the building's height. So the taller and taller you get on the structure, the larger pressures that you would get, and that's what Kz is taking care of. Now, Kzt is a topographic factor, and basically what that is if you have a building that for some reason is perched really high on top of a hill or really low in a valley, because of the topographical effects associated with wind, you can get some weird wind speed-up effects on your structure. It's basically a lookup, and for most cases that doesn't happen, and Kzt is taken to equal 1. So that's what we're going to do for in here. But if it's not, it's just a lookup. It's pretty straightforward. Now, KD is a wind directionality factor. First off, for buildings, it's always taken as a constant of 0.85. But what that does for it is it accounts for the wind striking the weakest side of the building, so it adjusts your wind speed accordingly. And then V is obviously your base wind speed. Now, I'm curious. This is a map of the United States. And what this is doing is reporting base wind speeds for different regions of the country. Now, most of the country is reporting a base wind speed of 115 miles per hour. Why is it that these regions around here are reporting values that are a little higher? Why would those regions report higher wind speeds? Hurricanes, exactly. So it makes sense then that, you know, if you're designing a building, let's say in Miami, you're going to use a higher wind speed that you would here, right? Make sense? Yes, sir.
Well, I guess there's a couple questions. How do the length of your piles relate to instances like place a very large building on top of a mountain or high wind speeds? Like, does it? Do you understand what I'm saying? Like,
No, not really.
okay, so like, yeah, so like, can you explain to me how it?
You're asking the structural engineer a geotech question?
Yeah. Like, does it?
Well, okay, let me say this. So the question was, what's the deal with basically wind and piles? Is that a, well, okay, so if you have wind striking a building, think of the building as if it's one large beam, okay? So if wind is striking the building, you know, it's almost like a big cantilevered beam. So part of the building would kind of be experiencing compression at the bottom, and then part of the building would experience tension. So it's possible that you could have maybe some uplift effects, you know, on your piles on this side of the building. But you also got to keep in mind we're talking about wind effects versus just the massive weight of the structure. So that really probably wouldn't happen under wind. Now under seismic, that's a different story, okay? Because seismic, you can generate some massive accelerations, and that's a different issue. But that, we're starting to go down the rabbit hole in the geotech aspects. I would just say in those instances, you're probably just going to have to use deeper piles. Deeper piles are going to generate a larger amount of skin friction to keep the building in place. Yeah, but I would argue that's more of a concern or a worry with seismic than it is with wind. Because think about it, when we look at seismic forces, what we're essentially doing is asking ourselves how many G's, if you will, the building has to respond to. So imagine if I took Smith Hall and I would, you know, just picked it up and held it like this, just held it right there. Okay, that building would be experiencing 1 G at that point because then it's just subjected to its own self-weight. Now, on some earthquake, you know, phenomena, you can get 2-3 G's, you know, very easily. So, you know, that's what we're talking about when I say, you know, it's much more concerned with seismic than it is with wind. I mean, yeah, you can have some strong forces when it comes to wind, but nothing like seismic. Is that a fair answer? And everybody else okay with that? Okay. Now, what I've got here, just a heads up going back to wind, is I'm reporting these base wind speeds in this map according to what's called risk category 2. And I think I should take a little bit and describe what risk categories are. So a lot of the environmental loads that you see in the spec, like earthquakes and snow and things like that, are a function of the designated risk category of a structure. And the easiest way to describe that is to say something like this. Which structure do you think is going to have a worse impact if it fails? A grain silo or a new trauma surgical wing of a hospital? Probably the hospital, right? See, think about it like this. If a grain silo fails, it sucks, but it's not going to impact a community like the failure of, let's say, a police station, okay? So certain structures have certain risk categories, and we rank them 1 to 4. Now, by and large, most structures that we design are risk category 2. but some of them can go in and out. So for instance, risk category 1 is structures that normally are unoccupied and would result in negligible risk to the public. So grain silos, barns, storage shelters, greenhouses, things like that. Those types of structures would be risk category 1. Now, risk category 3 are structures that house a large number of people in one place, or buildings that have people that may not have the ability to escape. So for instance, if you're designing, let's say, an elementary school, like that would definitely be a risk category 3 because they're children. They might not have the ease of escape, adults in a commercial office building or things like that. Also, large capacity structures like theaters. There's probably some buildings on campus that should be risk category 3 because of large lecture halls and things like that. Prisons, healthcare facilities, things like that. Risk category 4 is structures where their failure is not only going to impact the people in that building, but they're going to impact everybody. So 911 call centers, hospitals, fire stations, police stations, things like that. So depending on the type of structure that you're designing, your loads that you're applying to that structure are either increased or decreased depending upon the effects. Does that kind of make sense? For most cases, though, you're going to be in risk category 2, and that's what this map is reporting is risk category 2. Now, just the last thing that I guess I should mention is the effects of height. Depending upon the height or the height off of the ground of the point that you're looking at, the wind speed or the wind resulting wind pressures change. We calculate that through an exposure coefficient, KZ. It's really plug and chug. It's just a function of the exposure category and the risk category. Now, the exposure category. Exposure categories are essentially relate, okay, yeah, we've got a building in Huntington, West Virginia. Let's say we're designing a building here. What's going on around the building? So here's some ideas or some representations of different exposure categories. So for instance, exposure category B would be, an urban type area where, if wind strikes a building, yeah, it'll strike the building, but there's a lot of other stuff in the way. There's a lot of other structures and facilities in the way that might disturb that wind speed. Whereas exposure category C is almost like farmland or rural areas out in the middle of nowhere. I mean, think about it. If I had a 1,000-foot tall building, you think it's going to see different wind loading here versus here? So, I mean, it's a different story, okay? So depending upon where you're at, you're going to be either in exposure category B, exposure category C, or D, which would be right there along coastal regions. There isn't an exposure category A. It's basically just used for if you've got a really complex structure and you're using like wind tunnel testing to determine the loads and whatnot. So that isn't a typo. There isn't a B. Based on your exposure category, you have different gradient heights and exposure coefficients. And basically, all this means is if I'm in exposure category B, what this is saying is that the equation that I use for wind calculations is pretty much going to be accurate up until around 1,200 feet. Once you get past 1,200 feet, I mean, we're talking about a structure that's pretty complex, and it's time to start breaking out some more refined computational tools, some finite element stuff, maybe some wind tunnel testing to assess what's going on. I mean, if you're talking about a 1,200-foot structure, an estimate in the spec might not be the best assessment. You might need to do something a little more refined to ensure everything's happening, make sure that everything's happening within the assumptions that you're making. Sound good? All right. Let me go through a pretty basic example with you. So I've got just a regular old, let me ask, does that look like a brace frame or does that look like a moment frame? Moment frame, well, of course it says moment frame, but notice how there's no triangular braces inside the structure. So I've got, it's a 4-story building with the roof. So the first story would be the ground. I know that sometimes that can get kind of confusing because a lot of people think, ground and then first floor, or the ground is the first floor and the second story goes up. So I just sort of labeled it. So the second story, third story, fourth story, and the roof. And I've got different story heights just to make the calculations a little more, I don't want to say interesting, but just to give it a little bit of variability. Now, we want to determine the base wind pressures at each of these stories for this moment frame shown. So we're going to assume that it's a typical commercial office building in Huntington, West Virginia. So first off, because it's a typical office building and it's not a school or a hospital or anything like that, we can assume that the risk category of the structure is risk category 2. Okay? Plus, because we're designing this structure, we'll say it's sort of in the city limits. It's certainly not a rural area, so we'll just go ahead and say exposure category B. Okay? Sound good? The only other thing we need to take into account is that topographical coefficient. We'll assume that it's pretty flat, so we'll just take KZT to equal 1. All right? Now, one of the things about these specifications is they print off a map that looks something like this. And this is a pretty easy one to interpret, but some of the more difficult ones are things like the snow maps and the seismic maps, and it's really tough sometimes to determine like base wind speeds and things like that. Plus, if, we're lucky, we're right here, so I think, our base wind speed for risk category 2 is 115 miles per hour. That's pretty easy to see. But what if we're in, Virginia Beach or Manhattan or, New Orleans or something? Which one am I in? Am I in this region or in that region? Sometimes it's a little tough to interpret. Fortunately, I think there's a fair amount of engineers out there that recognize that. And there are a number of online tools that can help us determine base wind speeds pretty easily. And not just wind speeds, but snow loads and seismic loads and things like that. So I want to go to this website to determine base wind speeds. I have the link here as well. Let's see. Actually, I think I have to do that, and then there we go. Ugh. Internet Explorer. I don't like that, but you know what? I'm not using Internet Explorer. Okay. See, look, this is still loading, and this one's already loaded up. Okay, so this is an online calculator that'll help you determine wind speed. One of the things about it, though, is you need some information about the location that you're looking at. So you can find that information based on this just map that's been provided here. I think it's actually a little easier, though, using these types of websites to actually find the latitude and longitude of the location that you're looking at. Plus, we're going to be using some USGS tools to get ground accelerations for seismic. So I'd say the easiest way to determine the latitude and longitude is to use Google. So what I'm going to do is this, I'm going to go to Huntington, West Virginia, latitude and longitude, and then there we go. All right. So this is the latitude and longitude generally of Huntington. You could get a little more accurate if you want. You could find what's the latitude and longitude of Marshall or of this particular building. I don't think for wind speeds you really need to get more accurate than that. I doubt even in some of these higher wind regions that the wind speed appreciably changes from one side of the street to the other. In the end, our base wind speed in Huntington is generally going to be the same throughout. Now, our latitude and longitude here is 38.4192 degrees north and 82.4452 degrees west. Okay? So the way that we would enter this is, first off, let's copy and paste this here. So, scroll up. So this is our latitude, and then our longitude right here goes here, but we have to think, in terms of our coordinate systems. Let me see if I can draw right here. You have to think in terms of our coordinate systems. Oh, don't do this to me. Oh, of course. Oh, let's see. Of course, my screen had to fail too. Yeah. There we go. What the heck? Even though it wasn't really broken, All right. So we have north, south, west, East. So our north, we were what, 38 something degrees north, and what was it like? It was 81 something west. So 38 degrees north, we would treat that as positive because it's going up on the y-axis, but 81 degrees west, we treat that as negative because it's going left on the x-axis. Make sense? So when we go to our online, 82 degrees, sorry, we would put in a negative here. Then we get wind speed, and then this is what's spit out. So first off, does the map look right? I mean, this is West Virginia. There's Huntington about right there. And then risk category 2, our wind speed is 115 miles per hour. So this makes sense. That's a value that would be fairly reasonable. Sound good? All right. Okay. Okay. So let me go ahead and erase this and actually start to do this example a little more diligently. All right. So example 1A. So our base wind speed is 115 miles per hour. And we're going to say it's 115 miles per hour based on risk category 2. Again, if we were designing a hospital or a grain silo or something like that, it'd be different. Okay. Now, which exposure category do we have for the structure? Remind me. All right. Okay. So if we have exposure category B, that gives us a couple constants. So it gives us ZG and alpha. What are those? 1,200 feet and 7.0, right? Okay. Now we've got our topographical constant to equal 1, which again, that's largely always going to equal 1 unless you have a really weird, the building's on top of a hill or something. And also our directionality factor is going to be 0.85. Okay. So what we have to do in order to do this is we calculate a base wind pressure at each story of the building. So we would have to do this calculation, 4 times, one for each story. So because you're having to do this calculation over and over and over again, it's starting to sound like it's a nice Excel calculation, right? Nice repeated calc. We're going to do one of them by hand, and then I'll show you the Excel file that does them all. So let's consider the 4th story, and I just sort of picked the 4th story. What's that? Yes, sorry. I'll write that out a little. KZT equals 1. Bless you. What's that? Oh, I'm sorry. What's that? All right. So let's consider the 4th story. Now, the first thing we need to determine is Z. Now, Z is the height of the 4th story above the ground. So if I go back to the image here, so if we're looking at the 4th story, how would I determine the height above the ground? I'd say 12 plus 14 plus 15. So Z equals 12 feet plus 14 feet plus 15 feet, which comes out to what? 41. Okay. Now, we need the height in order to determine our KZ, and KZ is basically calculated using the following equations. So the idea is anytime you have a building that its height is less than or equal to 15 feet, we just use a constant wind pressure. I mean, think wind pressures are a function of the building's height, and if the height of the building is less than 15 feet, that's a pretty short building, so we just use a constant pressure and just go with it. But anytime the building's taller than that, we would compute it using the following expression. So 2.01 z over zg raised to the 2 over alpha. So make you all do a little bit of computations this morning. So kz equals 2.01. 2 over alpha is the exponent, so 2.01 raised to the what? You tell me. What's that? Well, yeah, but yeah, that's right. That's 2 over 7, and then I'm getting ahead of myself. The fraction inside is going to be what? 41 over 1200. So what's that come out to be? We'll say 3 decimal places. 765 or 766? All right, that's what you got? All right, okay. So that's kz. So we have, we think we have kz, we have kzt, we have kd, and we have our velocity. We can determine our wind pressure pretty easily. So we'll say wind pressure QZ is as follows. So QZ equals 0.00256 times, actually, let me write it out. So KZ, KZT, KD, V squared. So that's 0.00256 times 0.766. KZT is 1. KD is 0.85. And 115 squared will give us our answer in pounds per square foot. This 0.00256, it's part Bernoulli's equation, and it's part a unit conversion to convert miles per hour into pounds per square foot. $22.04. Anybody else get that? Everybody else get that? All right. That's not too bad, right? Pretty straightforward. All right. So let me show you something real quick. If you look on Blackboard, I posted the following Excel sheet. So let me zoom in a little bit, actually. So we'll auto-hide that. We'll zoom in a little bit. Okay, so I posted the following Excel sheet, and what it's doing is computing the wind pressure for every story of the building, and it's just doing the same calculation over again. It's really not that complicated. So the base wind speed is 115 miles per hour, the gradient height is 1,200 feet, and the exposure constant is 7. So what we've got here is this. So we've got the second floor is 12, the third floor is 12 plus 14, 12 plus 14 plus 15, and then 12 plus 14 plus 15 plus 12. You can see the deal. Okay. Now, KZT and KD, they're all 1 and 0.85. They're pretty simple. Now, let me illustrate sort of what's going on here. So I was going to throw if statements in, but I said, what the heck, let's just keep it simple. So this second floor, if you notice, the Z is under 15 feet. So it's 2.01 times 15 over 1,200 raised to the 2 over alpha. But everything else is Z over ZG raised to the 2 over alpha. So if you look, here's 15, and then there's the ZG. Sound good? So this is the one that we did. That's the one that we did right here. So if you look, we got the 0.766, we got the 22.04. We would just do the same thing over and over again. Sound good? So the way that we would use this is we'd say, all right, let's take each of those pressures, let's go into a program like RISA or something, build a big model of the structure, and then just put those pressures, those distributed loads on those floors, and then just run a RISA analysis. So you all have experience now with RISA since we did that last semester. So you would use that to generate your wind forces. Or if the structure was simple enough, you could analyze it by hand. So, sound good? All right. What's going on here? Oh, that's right. We got a few minutes and then it's time for concrete. Okay. So, anybody got any questions on this? Okay. Let me at least sort of introduce what's going on next. We're probably going to have to call it because of time and because of technical difficulties and whatnot. So, anybody have any questions about this? I just wanted to give you all a basic understanding of the map. Sound good? All right. So there's a couple things that I'm not going to talk about. One of the things I'm not talking about is that whole issue of positive and negative pressures inside a building. Remember the idea if I'm in, let's say, a tall building and it's a really windy day, sometimes the doors will want to slam shut or sometimes they'll just want to stay open and they won't close. It's because you can develop positive and negative internal pressures inside of the building due to wind. So sometimes you have to account for that when you're doing your frame analysis. Also, one of the things I didn't talk about was wind hitting the building in different directions. If you have a symmetric structure, that's usually not the biggest deal in the world. It's only when you have a structure that has a really weird shape to it, like an L-shaped building or something that has some weird profile, that sometimes you have to account for not only the the wind striking the building in different directions, but sometimes you've got the building and it may want to twist under the wind. Maybe it's hitting it this way and it's causing it to want to twist. But all in all, it's really just sort of plug and chug and pretty straightforward stuff. I want to at least introduce seismic forces to you, and then we'll probably delve into this on Friday. But seismic events are the other big lateral effect that buildings experience, but they don't apply a force to the building, they apply an acceleration. I mean, going back to the example of being in the car, if you're in a car and your friend's doing 60 miles an hour or what have you, and they suddenly hit the brakes, you fling forward, right? Now, the reason that happens is because your body underwent a sudden change in acceleration, okay? And your hips didn't have the lateral stability to hold you back, so you just fling forward, right? Okay. Now, because of that, we insert a system into the car that's meant to hold you back, and that system is the seat belt. So the seat belt is experiencing a load based on your mass undergoing a certain acceleration. Make sense? Same story with an earthquake. The building experiences an earthquake, so the ground is moving like this. It's accelerating the structure. The structure is undergoing a given acceleration. So force equals mass times acceleration. Your building or your lateral system in your building, I should say, has to be able to withstand those resulting forces. Okay. Now, the general procedure for seismic loads tends to work something like this. So the first thing you have to determine is what's called the seismic response spectrum, and that's a really fancy term for just your ground accelerations, which is going to be a function of where you're at. You're going to have different ground accelerations in Huntington than you would in, say, Los Angeles. Los Angeles is going to have much larger ground accelerations just because it's a higher seismic zone. You're then going to have to determine the building's period of vibration, which we'll talk a little bit about that next time, but basically it's how the building naturally wants to vibrate under a free vibration event. And then we determine the seismic response, how many Gs, if you will, the building should be responsible for in an earthquake. Once we get that, we just take that total force and just distribute it to each story, and then we'd run another RISA analysis. And that's basically it. Seismic forces are a little more involved than wind, but in practice, it really is just plug and chug. And we'll probably spend all day on Friday discussing, how exactly do we go about that. The only other point I'll show you is this. This is from the USGS, the U.S. Geological Survey, and they look at a number of things, but one of the things that they produce is seismic hazard levels across the United States. And I know a lot of times, you know, especially in our region of the country, a lot of engineers, they go, we're in West Virginia, why do we care about earthquakes? You know, it's not a matter of whether or not we experience earthquakes or whatnot. It's more of a matter of our risk of damage and our risk of danger if an earthquake were to occur. I mean, if you look here, this seismic hazard level, I mean, this is Western Kentucky, right? And this is just as large of a seismic hazard level as out in LA, okay? So if you're designing a building out in that region, you got to design it just the same as you would out in LA, you know? A lot of people don't realize that, but it's all about risk, okay? If that region were to go because it lies along a fault line, it would be bad, okay? So we have to address that accordingly. Does that sound good? All right. So next time we'll talk about exactly how to determine seismic response coefficients. We're going to do something very similar using an online tool, assuming all the technology works today. So that's all I got for today. Real quick, if you haven't already gotten your manual, you really need to do so as soon as possible, and that's all there is. Make sure you get handouts if you haven't already done so, and the sign-in sheet. Hold on for 1 second. All right, we'll see you.